Hello students, so in this lecture we will discuss about FCC nanoparticles. Now why we are only focusing on FCC nanoparticles? The reason is that most metals in solid form are in the FCC. Like if you take the closed pack lattices, for example in case of silver or gold, silver or aluminium, then copper, cobalt, platinum, lead. All these are in FCC form, and also there are some rare gases like neon, argon, krypton, and xenon. They are also in the FCC state. Whereas apart from that, other metals, common metals like magnesium, rhodium, sorry, lithium, yttrium, and zinc. They are in HCP state. These are all in FCC. These are all in FCC. Now these FCC and HCP, they come under the close packed lattices. Whereas there are other metallic metals which are not so close packed, and like chromium, lithium, strontium, they are having the structure BCC. So mainly when we talk about close packed structures, we mainly consider the FCC and the HCP structures. Now in the both of these cases, the coordination number, that's the number of nearest neighbors, is 12. So that is why if we now look into the structure where there are say 13 atoms, so that means one atom surrounded by 12 coordination number atoms. So this will form the smallest theoretical nanoparticle. Smallest theoretical nanoparticle for an FCC lattice. And it is also called the FCC unit cell. So they form a shape something like this. You have 4 atoms at the top and 4 atoms below, and we have 2 here, 6 atoms here. So that makes it 14 atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 atoms. So it forms a 14-sided is. Fourteen-sided polyhedra. And they are known by the following name: deca, decacerahedron, the 14-sided polyhedra. And they're generated by atoms with planar faces. So in the 14-sided polyhedra, we have 6 squares and 8 equilateral triangles. Now, if another group of 42 atoms is layered upon the 13 atom nanoparticle, so we have a 13 atom nanoparticle. If another 42 atoms are added to it, so we form 55 atom nanoparticle. 13 atoms because 4 sides, so we add 4 13 atoms each to one side, so 13 into 4. Oh no, sorry, that is not the case. It becomes 52 then. So 42 atoms are added. So we have something called 55 atom nanoparticle. So it will have the same decatetrahedron shape. So the sequence is like that. For example, when we start with one atom, of course this is the smallest nanoparticle, but it's not, we cannot actually practically have one atom. Then we have 13 atoms added to it. Then we have 55 atoms, add 42 atoms more, and then 147, then 309, and then we can have lastly 561 atoms added. And these atoms, these numbers, they are known as structural magic numbers. Now, how do we arrive at this number? I was wrong in the fact that when I said 13 atoms at 4 sides, there is actually a relation with the number of atoms and for n layers. So if we consider that we would like to have n layers, and if n is the number of atoms, then relationship is n is equal to 1/3 10 n cube minus 15 n square plus 11 n minus 3. So let's use it. For example, if you take n is equal to 1, right? So the value of n will be 1/3 into 10 minus 13 plus 11 minus 3. It will come as 1/3 into 21 oh sorry, it's 15 not 30. Minus 18. So it is okay. Now another let's we'll do it. Another aspect to this is there are n atoms at the surface also. N atom at the surface. This is equal to 10n square minus 20n plus 12. So taking n is equal to 1, we get n surface is equal to 10 minus 20 plus 12. So that makes it 2 atoms at the surface. And here we get 1/3 into 10 plus 11 is 21 minus 18, so that is equal to approximately 1. So 1 plus 2 becomes 3. Still doing something wrong here. N is equal to 1. Let's use it again. N 1/3 10n cube minus 15n square plus 11n minus 3. So let's take n is equal to, if we take n is equal to 2, then let's take what is going to happen. This will be 1/3 into 10 into 10 into 8 minus 15 into 4 plus 11 into 2 minus 3. So that will be equal to again 1/3 80 minus 60 plus 22 minus 3 to 1/3 20 plus 22 minus 3 be 1/3 39 by 3, that makes it 13. Okay, so the first number of atoms that will have, it is going to be a 2-layered structure. Okay, so the 13-sided nanoparticle that we initially called, it is actually a two-layered structure considering 3 atoms. And if we consider the surface atoms, like the formula for surface atoms is n surface is equal to 10 n square minus 20n plus 12. So if we take n is equal to 2 here, so the n surface atoms is 10 into 4 minus 20 into 2 plus 12, so that is equal to 40 minus 40 plus 12, so that is equal to 12 atoms on the surface. Okay. Now the diameter of each nanoparticle is given as 2n minus 1 into d, where d is the distance between the centers of nearest atoms. The distance between nearest atoms and is usually equal to a by root 2. That is very typical of an FCC lattice, where a is the lattice constant. Now if we move to an HCP lattice or HCP nanoparticle, then the number becomes 113, but instead of 55 we will have 57, a slight change. Then we will have 153, 321 and 581. Remember that for an FCC we had n is equal to 113, so initial two numbers were same. Later on it was so we'll use a different color here. It was 55, and then it was 147, then 309, and then it was 561. So we take the difference between this one and this one. So initial, so take it as delta n between FCC n. So it is 2, 57, 55, then it is 6, then it is 12, and it is 20. 2, 6, 12 and 20. So this was for n is equal to 1 layer, n is equal to 2 layers, n is equal to 3 layer, 4 layer, 5 layer and 6 layer. Okay, so that is why we were not getting the value for n is equal to 1. We obtained the value of n as 1/3 into 3, that was equal to 1. And for n is equal to 2, we obtained 1/3 into 39, that was equal to 13. So the n is this number of layers. This is the number of layers. So the difference we are having in the third layer is n is equal to 2, then it is 6, then it is 12 and 20. I would like you to give a task that then find out the expression of n and n, find the expression of n, only n, for the HCP lattice. N for HCP, expression of the light, we have n is equal to 1/3 10n cube minus 15n plus 11n minus 3. This was for the FCC lattice. I would like you to find out n for the HCP lattice. This is an assignment. Now let's go to some examples. This is a very common FCC nanoparticle, gold 55, and it is very reactive. And it has also got a short lifetime. And it can be stabilized by using an organic group. That you have AU55, then you form EPH3, 12Cl16. By using this organic group, you can stabilize this AU nanoparticle, and the diameter is around 1.4 nanometer. Other examples of FCC nanoparticles are platinum 309 and palladium 561, and they're also stabilized by an organic group. Like in this case, it is stabilized by 110 phenanthroline, 110 phenanthroline 36 O30 and in this case it is again the same thing, 110 phenanthroline and 36 O200. Now the magic numbers that we have discussed, like for FCT is 11355 and for an HCP it is 11357 these magic numbers they arise because of the following reasons: because of the minimum volume, then because of minimum volume, then maximum density, and then spherical shape, approximate spherical shape, and close pack structures. So this is the reason we get these following numbers. So please do the assignment on finding out the expression of n and number of layers, that is small n, for an HCP.